In this video, we're going to consider the magnetic field of a solenoid. So first we should define what a solenoid is. A solenoid is a coil of wire that might look something like a stretched slinky, or maybe even a compact slinky because they're often very, very tightly wound. The idea is that within a solenoid, the current flows around and around in this kind of spiral or helical structure. And that can create very strong magnetic fields in the center of the solenoid. And this is what we want to explore in this video. The solenoid that we have here has current running into the board at the top and out of the board at the bottom. So the current is kind of coming out of the board, looping around, coming back into the board in this helical structure. Now, of course, we would need one end of this to be hooked up to a battery, or both ends to be hooked up to a battery so that their actual current could flow. But we're not going to worry about actually drawing the battery here. We're just going to assume, yes, this is hooked up to a battery. There is current flowing through it in a given direction. Now let's try to qualitatively assess what the magnetic field of a solenoid should look like. So I've removed the actual wires here from our picture just to simplify everything as much as possible. All I have are the currents moving in at the top of the wire and the currents moving out of the board at the bottom of the wire, and I've removed the actual spiraling. It's still there. I just didn't draw it so that we could have a more clear picture of the magnetic field. So in this solenoid, we have magnetic or current going into the board and then out of the board at the bottom, into the board at the top, out of the board at the bottom, spiraling like so. Okay, let's just pick an arbitrary point near the center of the solenoid and see what the magnetic field at that point looks like. Now I've labeled 3 individual pieces of the solenoid wire, and what we're going to try to do is figure out what the magnetic field due to each of these individual pieces of wire looks like at this point here. So first, let's imagine that I pick a point, sorry about that. Let's imagine that I pick a point directly in between wires 1 and 2. And I know it's not exactly true, but imagine that these two are directly above or below one another such that they form kind of a straight line up and down. Okay, to find the direction of the magnetic field due to wires 1 and 2, I can actually just use my right-hand rule that we found for infinitely long straight wires. That is, my thumb points in the direction of the current and my fingers curl in the direction that the magnetic field curls around the wire. So if I do that for point 1, well, my thumb points into the board and my fingers curl in the direction of the magnetic field due to that piece of wire. Now, I realize that this is not an infinitely long straight piece of wire, but even if it's just a little short piece of wire, which it is, I'm just taking an infinitesimal bit out of the top of my solenoid here, the right-hand rule still works for the direction of the field generated by that current. Okay, so the magnetic field here should be moving to the left at this point. I'll write that as some little piece of magnetic field, B1. B2, well, my thumb points in the direction of current 2. My fingers curl in the direction that the field curls. Right above wire 2, I get some magnetic field pointing to the left, B2. So together, 1 and 2 give me a total field to the left. Okay. So I'm going to erase this now, but we're just going to remember that these 2 wires gave me a field when I summed them up, just pointing to the left. Okay, now let's do the same thing for this point using wire 3 and wire 4. Okay, well, if I do this for wire 3, thumb points into the board, my fingers curl around, and so if I kind of make a circle around wire 3, like so, at this point, I'm going to get a magnetic field, call it B3, that is going to point up and to the left. finger points in, or my thumb points into the board and my fingers curl around this way, so my magnetic field is going to point up and to the left for B3. If I do the same thing for my little chunk of current coming out of the board 4, I will get another, I'll put it in a different color here, I'll get another circle here, right, surrounding B4, and at my point here, I will have a magnetic field pointing down and to the left due to wire 4. Now, if I add these two vectorially, like so, so instead of drawing B4 from the point, I use my tip to tail method, where I draw the first vector and then I draw the second vector from the tip of the first vector. I get a total magnetic field vector that points, I'll call it B34, that points straight to the left, right? These two magnetic fields, the one due to wire 3 and due to wire 4, the Y components have canceled out and only the X component is left, meaning that I get a total electric field to the left due to 3 and 4. Now, I should make a brief note here. In general, I try to draw the length of my magnetic field vectors in proportion to the magnetic field strength. But here, I made 3 and 4 the same length. That was important. But I didn't make 3 and 4 shorter than 1 and 2, where they clearly should be, because wire 1 and wire 2 are clearly closer to my point, therefore would exert a stronger magnetic field at that point than 3 and 4. But what I'm looking for at the moment is just, what is the direction of the magnetic field? Well, 3 and 4 give me a magnetic field together to the left. 1 and 2 also combine to give me a magnetic field to the left. In total, then, I can say that I could make the same argument for these two together, that their Y components would cancel and their X components would add. Likewise for these as well. So what I can say is, near the center of my solenoid, I have nice straight magnetic field lines pointing to the left here. And I'll just draw 3 of them. So my solenoid, inside of the solenoid, has generated a nice, consistent magnetic field pointing to the left. Now, if I get too close to one of these individual wires, I will get some magnetic field lines circling the wires themselves, but that isn't really the effect that we're interested in for this video, so we're not going to worry about magnetic field lines very, very close to the individual solenoid wires. We're going to consider the total magnetic field kind of near the center of the solenoid. Now let's look at what the magnetic field looks like outside of the solenoid. So we're going to do exactly the same type of analysis. We'll look at 1 and 2 and see what the combined magnetic field due to these two wires, or these two segments of wire, are up here. Okay, so at this point, if I do my analysis on wire 1, well, my thumb points into the board and my fingers curl in the direction of the magnetic field. My fingers are curling to the right above the wire, so I get some magnetic field number 1 pointing to the right at this point. If I consider wire 2, thumb comes out of the board, my fingers are curling in the opposite direction, so I get some field B2, which points in the opposite direction. Now, the magnetic field due to wire 2 is clearly going to be weaker than the magnetic field due to wire 1. Why? Well, wire 1 is closer and is carrying the same current, because the current is just looping around, so every point in my wire must be carrying the same current. So I'm going to get a slightly weaker magnetic field due to wire 2 than wire 1, pointing in the opposite direction. In total, I'm going to get a magnetic field that points to the right. Here, I'll call it B12, that is weaker than the internal magnetic field by a significant amount. We could do the same analysis of this point here using our other locations. And what you'll actually find is if you compare 3 and 5, so the magnetic field to 3 and 5 at this point, I'll just do it quickly. Due to 3, it should point something like this, because that is the part of the circle that my this point is on. And for 5, it should point something like this. And if you add them together, you get a magnetic field to the right. This is B35. So again, we have parts of the wires that are canceling each other. The Y components are canceling, the X components are adding, so we're getting magnetic field to the left in total. You could do 4 and what I'll call 6 as well, and you would get the same idea. 4 and 6 would move to the left, but again, their Y components would cancel, their X components would add. And so the combination of 3, 5, and 4, 6 would give you a weaker magnetic field to the right here. So in general, the magnetic field outside of the wire point, or the solenoid, points in the opposite direction of the magnetic field inside of the solenoid and is generally quite weak in comparison with the magnetic field near the center. Now, if we want to draw the magnetic field lines of the solenoid, we can just connect our field lines up top around through loops to our field lines in the bottom. So I can draw one here, like so. So the magnetic fields move outside of the solenoid to the right and then through the center. And then maybe I'll draw 2 more field lines here near the center that loop out and around, like so. And then this one would be kind of outside of the board there. Notice that the field lines in the center are very, very dense, indicating a strong magnetic field, and the field lines outside are very dilute, indicating a weak magnetic field. If you remember, this actually looks exactly like the magnetic field of, say, a bar magnet. Remember that if we have a bar magnet, our north end and our south end, I'll draw it in a different color here, the magnetic field lines of a bar magnet come out of the north end and go into the south end and actually travel all the way through the bar magnet. So, bar magnet magnetic fields look just like the magnetic fields of solenoids. So this here would be kind of the north end of the solenoid, because that is the end that the magnetic fields come out of. And this over here would be the south end of the solenoid, the end where the magnetic fields go in. Now we are going to combine our knowledge of the shape of the magnetic field with our knowledge of Ampere's law in order to actually find an equation for the magnitude of the magnetic field near the center of this solenoid. So what we have is we have an Amperian loop where we have put arrows in the direction that we are going to take this integral. So remember that Ampere's law is the integral around a closed loop of the magnetic field dotted with the little dLs, the little distances around the loop. So we're going to add up the dot product of the magnetic field with the length vector around the loop. Now, this is equal to mu naught times I enclosed. We will get to the right-hand side of this equation in a minute, but first we are going to do the left-hand side. So what we're going to do is we are going to break our loop up into 4 different segments. We have the left-hand side, the top, the right-hand side, and the bottom. Okay, so in each of these sections, we are going to have some little dl vector, right? So this, for example, part 1 is broken up into all of these little dl vectors that each point in the direction that I am integrating around the loop. And so along this side here, all of my dl vectors point up. Well, if you notice, my magnetic field is perpendicular or very close to perpendicular to dl throughout the entire distance here, right? So down here, if I had another magnetic field line, say that moved, through this part, my magnetic field is perpendicular to my dl vector. Up here, my magnetic field line is perpendicular to my dl vector. So in general, when I take this dot product, the magnetic field dotted with dl all the way up this side, I'm going to get 0 because the dot product of two perpendicular vectors is always 0. Okay, so for this left side here, I can say that the integral of the magnetic field dotted with dl, or I don't even have to take the integral, just each of my magnetic fields dotted with a little dl is going to be 0 because they are perpendicular for the entire length. I can make exactly the same argument about 3. I have magnetic fields. They are going to be perpendicular to my little dl vectors. In this case, my dl vectors are going to be pointing down instead of up, but the same idea. My magnetic field is either going to be pointing to the left or to the right. So my integral of b dot dl along the right-hand side here is also going to be 0. Now, for number 2, my argument is that the magnetic field outside here is very, very weak compared to the magnetic field inside of the solenoid itself, and therefore I can say that the magnetic field is approximately 0. This is not technically exactly true, but as long as it is a very small number in comparison with the dot product inside of the Amperian loop, it's not going to make a difference, right? So say that this integral here, this b dot dl, so I'll put an integral here. So say that the integral of b dot dl along this line here is 1. Well, okay, that's fine. If the integral inside is 10,000, then the sum of this integral and this integral is still basically 10,000, right? This doesn't have to be exactly 0 for me to approximate it as 0, as long as it doesn't change my answer by a significant amount. Okay, so we're going to argue basically that the magnetic field out here is very weak, and therefore my integral of b dot dl along this line here is approximately 0. Okay, so now what we can do is look at item 4. This is going to be the only non-zero one. Well, all the other ones are 0, so we better get something that's non-zero, right? Okay, well here we have a dl vector. You can see that it's pointing to the left here. So what we're going to do is we're going to take our magnetic field pointing to the left, dot it with our dl vector also pointing to the left, and then integrate over my length. Well, the magnetic field, as I have argued, inside of the solenoid is not changing. It is effectively constant. So I have this constant magnetic field dotted with dl. Because they point in the same direction, their dot product is simply their normal product. The dot product of two vectors that point in the same direction is just equal to the product of the two magnitudes. That is the magnitude of b multiplied by the magnitude of dl. Because the magnetic field isn't changing inside of my Amperian loop or along this line here, I can pull that constant magnetic field outside and then just integrate over dl. Well, the integral of dl is just the integral of this length. That is, it's just how long is this bottom side of my loop. So in the end, what I have is that the integral of b dot dl along this bottom side, part 4, is just the magnitude of the magnetic field multiplied by the length. Now that we've analyzed the integral of b dot dl along the 4 portions of our loop, we are ready to think about the right-hand side of Ampere's law. So simply writing down the only non-zero portion of our integral of b dot dl, which is the component along our bottom part of the loop here, we can write down that b times l equals mu naught multiplied by I enclosed, where again, I enclosed is the total current enclosed within our Amperian loop. In this case, we have 1, 2, 3 currents passing into the board inside of our Amperian loop. Okay, so what we can do is we can write the I enclosed as n, where n is the number of turns that are inside of our Amperian loop, multiplied by the current I flowing through the loop. So just to be very clear, I enclosed is the sum of all of these individual currents, where I itself is the 5 amps of current that is flowing through the solenoid, or whatever number of amps it is the current that flows through the entire solenoid. So n times I would be 1, 2, 3 in this case, multiplied by 5 amps, say, which would be the current flowing through the solenoid, where 5 amps is just a number I made up that has units of amps. Okay, so our I enclosed, where this is an L, not another E, is equal to the number of loops, the number of turns of the solenoid that the Amperian loop encloses, and I is the current flowing through the solenoid. Rewriting it this way, we can write the magnitude of our magnetic field is equal to mu naught n divided by L multiplied by I. Now we only have one more step in order to get to our final form for the magnitude of the magnetic field at the center of a solenoid. So what we're going to do is introduce a new variable, which is the total number of turns of the solenoid divided by the total length of the solenoid. Now, I understand that when we derived this, we only looked at the number of loops inside of our Amperian loop, but the N over L for this section of the solenoid, assuming that the loop density doesn't change, that is the number of loops per meter, doesn't change throughout, should be the same for this section of the solenoid as it would be for the entire thing. So we can just define N as the number of loops divided by the length for the entire solenoid, the loop density or turn density of the solenoid. And then we can write B equals mu naught times the turn density multiplied by I. Just to give you a sense of what this turn density means, I have a slinky. So when the slinky is barely stretched, per distance I have a lot of turns. My little n would be a large number for this type of a solenoid where I have a lot of turns per distance. I could take the same number of turns and stretch them out. Now I've increased the denominator, I've increased the length without changing the number of turns because I haven't added any turns between my hands here. Now I have a much smaller loop density. So the more tightly packed my turns of the solenoid are, the bigger little n will be, and therefore the larger the magnetic field will be for a given current flowing through it. Now let's do a quick example of using this formula. So our problem setup is that a solenoid has 250 turns and a length of 10 centimeters. If a 5 amp current runs through the solenoid, what is the magnitude of the magnetic field at the center? Okay, well, I've drawn the solenoid here. These are the loops moving through. Because this question doesn't tell me any type of an orientation of the solenoid or the current through the solenoid, I have no way of knowing which direction the current is flowing. But since all I'm looking for is a magnitude of the magnetic field anyway, it doesn't actually matter. Okay, so the length of my solenoid is 0.1 meters. As always, it's important to work in base units, meters being the base unit for length here. What we're going to do is we're going to compute our number density for the turns of the solenoid. So it is 2,500 turns per meter. That is 250 divided by 0.1. Plugging that into my magnetic field equation here, I get a magnetic field of 0.16 Tesla as the magnitude. As a final note, I just wanted to give you a shorthand for actually finding the direction of the magnetic field at the center of a solenoid. Again, this problem didn't give us any hints about what the direction of the current flow was, therefore, just based on this information, we could not have found a direction for the magnetic field. However, I just made up a direction for the current. So these blue marks here are the current direction. So the current is flowing out of the board on the bottom and into the board on the top. And we can use actually the same right-hand rule that we use for current loops to find the direction of the magnetic field inside of a solenoid, because what is a solenoid if not a collection of current loops? As a reminder, that right-hand rule is that our fingers curl in the direction that the current flows. So that is into the board on the top and out of the board on the bottom. And our thumb points in the direction of the magnetic field at the center of the solenoid. So here we have our current curling this way and our magnetic field flowing through the center.